So in this video, I want to do an example of before and after framing, and it's actually an example that, although it's very similar to the kinds of examples that you typically see in collisions, it's one that really makes a point about before and after that I think is a little different from the way you talk about collisions. So the example is one of a gravitational slingshot, and so I'm going to imagine I have a planet here. The planet has a mass m, and it's traveling to the left with some velocity, I'll say v, or v sub p. Right, this is the mass of the planet, and I've got a spacecraft here that's traveling to the right with some velocity v sub s and a mass m sub s. And what I'd like to have happen is for this spacecraft to come orbit around the planet and then exit back out, going in the opposite direction, but hopefully at a much higher speed than it was traveling originally. Right? Now, you might look at that and say that actually seems like it's really problematic because I've got a larger speed here than here, so that would say that I've actually somehow picked up extra energy in this system. And the reason why that's not actually the case is that although the speed of the planet of the satellite increases, there's actually a commensurate loss of energy from the planet. So the way a gravitational slingshot works is actually that you're pouring energy from the planet into the satellite. So let's sort of set that up and think about that, right? I'm thinking about this in a sort of before and after framing. So this is kind of what things look like before, right? After, I've got the satellite moving at some new velocity to the left, right? It's still the same mass of the satellite, and of course after, the planet will in principle be moving at a slightly different velocity to the left as well. So this is my after situation. And during the time that the planet and the satellite interact, that's going to be a fairly complicated dynamics problem, right? I mean, I know I could simulate that if I needed to, but I certainly could learn something by asking the before and after framing, where I think about before and after as being both before I'm a long ways away from the planet, so the potential energy of the planet-satellite interaction is low, and after I'm a long ways away from the planet, so the potential energy of the interaction between the satellite or spacecraft or whatever S stands for is small as well. Okay, so in this particular interaction, there are a couple of things that are conserved. One of the things that must be conserved is the energy, total energy of the system. Right? I'm assuming that that there's nothing else around. There just is this large planet that's traveling along and the satellite that slingshots around the planet. So to that extent, there aren't any energy flows into or out of this system. My system boundary includes both objects, and I'm not losing any energy. Right? A second thing that's conserved here is the momentum of the system. Right? There are no forces that are crossing the system boundary, so the total momentum of the system must be conserved. I could also say that actually the angular momentum of the system is conserved as well, right? There are no external torques acting on the system, so actually the angular momentum is conserved as well. Since I'm going to think about both of these things as being particles, that's maybe not super useful. In fact, when I think about them just being particles and I don't take into account any rotational effects, the conservation of momentum and the conservation of angular momentum end up being fairly redundant with each other. So I'm just going to concentrate on energy and momentum. All right, so at this point I can now say things like, okay, what's my initial energy for the system, and what's my final energy for the system, and those two have to be equal to each other, right? And by the same token, I should be able to ask the question, what's my initial momentum for the system and my final momentum for the system, and those two things have to be equal to each other, right? Well, my initial energy for the system is 1/2 the mass of the satellite times the velocity of the satellite squared plus 1/2 the mass of the planet times the velocity of the planet squared, right? And by the same token, the final energy is 1/2 the mass times the final velocity of the satellite squared plus 1/2 the mass of the planet times the final velocity of the planet squared. Okay. Similarly, if I think about the momentums, the momentum in the initial case is going to be plus the mass of the satellite times the velocity of the satellite in the I hat direction minus the mass of the planet times the initial velocity of the planet in the I hat direction, right? And that's got to be equal to the mass of the satellite times the final velocity of the satellite in the I hat direction, and I'm going to define that as being negative because I'm interested in how big that is. So I'm going to say that VFS is a positive number, plus whatever the mass of the planet is times the velocity of the final velocity of the planet in the I hat direction. Okay? And at this point, I can just make the observation that this is a soluble problem, right? And the reason I can make that observation is I actually have two things that I know, right? I know what the initial velocity of the satellite is, and I know what the initial velocity of the planet is. And two things I don't know. I don't know what the final velocity of the satellite is, and I don't know what the final velocity of the planet is. So I have two equations and two unknowns. And to a certain extent, this now becomes a sort of exercise in algebra. And since I'm not particularly interested in doing algebra on a video, particularly because I will inevitably make mistakes 3 or 4 times before I get it right, I think I will leave it for you as an exercise to actually do the algebra to show that you can actually solve for what the final velocity of the satellite is and what the final velocity of the planet is. But what you will find that's pretty interesting is that the final velocity of the satellite is quite a bit larger than the initial velocity of the satellite. And the reason for that has to do with the fact that the planet is so much more massive than the satellite.